Ever wondered how machines can learn? How a simple set of numbers can make intelligent decisions? Hello everyone, I'm Rebar. Today we're diving into the world of neural networks, but with a twist. We're not using Python, TensorFlow, or any fancy libraries. Instead, we are building our neural network from scratch in C++, just pure C++ magic. To keep things simple but exciting, we'll train our model to learn the XOR function, a classic problem in AI. By the end of this video, you'll understand how neural networks work under the hood, and you'll have a fully functional C++ implementation. So grab a cup of coffee, fire up your C++ compiler, and let's dive in. Alright, before we start building our neural network, let's break down the essential header files we'll be using in our C++ code. These libraries provide the necessary tools for mathematical operations, data handling, and input-output functions. Let's go through them one by one. Here's the first one, hash include IOStream. Allows us to print output and interact with the console. Next we have hash include vector. Instead of using raw arrays, we use vectors to dynamically store and manipulate data. This is crucial for handling weights, biases, and layers in our neural network. Then we have hash include cmath. Provides math functions like exponentials and powers. And the last one, hash include cstdlib. Used for random number generation. We'll use it to initializing weights. And here I'm gonna use std namespace using namespace std. To avoid writing std : before standard library components like vector and cout. Now let's talk about activation functions, one of the most important parts of a neural network. But why do we need them? Without activation functions, a neural network would behave just like a linear equation, which means it wouldn't be able to learn complex patterns. Activation functions introduce nonlinearity, allowing our model to learn and adapt to intricate relationships, like solving XOR. Now let's implement the activation functions. First we have the ReLU, rectified linear unit function. And here I'm gonna say double ReLU, and it takes double x, and it will return inside parentheses x greater than 0, question mark, x colon 0. It's simple. If the input x is greater than 0, it returns x itself. Otherwise, it returns 0. This helps the network focus only on positive values, making training faster. Then we have its derivative. Double ReLU underscore derivative, and it takes double x, and it will return inside parentheses x greater than 0, question mark, 1, colon 0. But why do we need this? Because in backpropagation, we update weights using gradients. For ReLU, if x is greater than 0, the derivative is 1. Otherwise, it's 0, meaning neurons with negative inputs don't contribute to learning. Next, we have the sigmoid function, which is perfect for problems like XOR. And here we say double sigmoid, and it takes double x, and it will return 1 divided by, inside parentheses, 1 plus xbuff negative x. The sigmoid function maps any value between 0 and 1, making it great for probability-based outputs. And its derivative, double sigmoid underscore derivative, and it takes double x and it will return sigmoid x times, inside parentheses, 1 minus sigmoid x. This helps us adjust our weights efficiently during backpropagation. Backpropagation, short for backward propagation of errors, is an algorithm used to train artificial neural networks by adjusting weights to minimize error or difference between the model's prediction and the actual value, that true value. Is the key to how neural networks learn from data. Alright, now I want to create the loss function because we need a way to measure how good or bad our neural network's predicted values are. A loss function tells us how far off our predictions are from the actual values. The goal of training is to minimize this loss so that our neural network learns to make better predictions over time. Okay, let's do it. And here I'm going to say double mean squared error, and it takes vector double predictions and vector double targets, the actual values. Then inside the function, double sum equals 0. We initialize this variable to store the total squared error. It starts at 0 and will accumulate squared differences as we loop through the predictions. And here is the loop for size underscore t, I equals 0, and I less than predictions dot size and I plus plus. This for loop iterates over all elements in the predictions vector, and for each prediction we calculate the squared error like this: sum plus equals POW predictions square braces I minus targets square braces I and 2. This line computes the difference between the predicted value and the actual target. We squared this difference using POW function or power function, and we add this squared value to sum. Finally, we return the mean squared error. Return sum divided by predictions.size. And this gives us an average measure of how far off the predictions are from the actual values. Now it's time to put everything together and build our neural network. We'll create a neural network class that includes weight initialization, forward propagation, prediction, and training using backpropagation. Let's break it down step by step. We start by defining our class. Class neural network. Then we say public, and here we declare two sets of weights, weights 1 and weights 2. Vector, vector, double, weights 1 and weights 2. And two bias vectors, bias 1 and bias 2. Vector, double, bias 1 and bias 2. These are essential for our input to hidden and hidden to output transformations. If you want to know about neurons, weights, and biases, please watch this video. You can find the link in the description below. Okay, let's create the constructor. Neural network, and it takes int input size and int hidden size and int output size. In the constructor, we initialize the size of our weight matrices and bias vectors based on the number of input, hidden, and output neurons. And here we say weights1 dot resize input size vector double inside parentheses hidden size. Weights1 is a 2D vector, a matrix that stores the weights between the input layer and the hidden layer. And the resize method in C++ is used to change the size of a vector dynamically. It allows you to either increase or decrease the number of elements while preserving existing values. Next, we say weights2 dot resize hidden size and vector double inside parentheses output size. Weights2 is also a 2D vector, a matrix that stores the weights between the hidden layer and the output layer. Then we say bias1 dot resize hidden size comma 0.1. Bias1 is a 1D vector that stores the bias values for each neuron in the hidden layer. The biases start with a small positive value, 0.1, to help prevent dead neurons. Next we say bias2 dot resize output size and 0.1. Bias2 is also a 1D vector that stores the bias values for the output layer. Finally, we call init weights to randomly initialize the weights. And here we say init weights, which will create it in a minute. Okay, let's create the init weights method. Void init weights. And inside the method we say for arrow reference operator row colon weights 1. This loop iterates over each row, each input neuron's connections to hidden neurons. And arrow lets the compiler deduce the correct type, vector double. And reference operator row is a reference, meaning we directly modify weights 1, not a copy. Inside this loop, we have another loop, for double reference operator w colon row. Each row is a vector of weights because weights1 is a 2D vector, a matrix, connecting an input neuron to all hidden neurons. This loop iterates over each weight w in the row. Next we say w equals double rand divided by rand underscore max minus 0.5. Rand generates a random integer between 0 and rand underscore max. And the rand underscore max is a maximum value that can be returned by the rand function. Rand divided by rand max produces a random decimal between 0.0 and 1.0. Subtracting 0.5 shifts the range to negative 0.5 and 0.5, ensuring weights start as a small positive or negative values. Now we do the same for weights 2. For arrow, reference operator, row, colon, weights 2. And for double, reference operator w, colon, row, and w equals double rand divided by rand underscore max minus 0.5. This is identical to the first loop, but it initializes weights 2, which connects the hidden layer to the output layer. So the init weights method assigns random values to all weights, ranging between negative 0.5 and 0.5. This randomness is crucial, because if all weights start the same, the network won't learn effectively. Now let's implement and break down forward propagation, the process where our network takes an input and predicts an output. This method performs forward propagation in the neural network, and it takes two arguments. So here we say vector double forward, and it takes vector double input and vector double reference operator hidden layer. The input is a vector of input values for XOR training, and the hidden layer is a reference to a vector that stores the hidden layer's activations. And this method returns a vector of output values after applying activations. Next we say hidden layer dot assign weights 1 square braces 0 dot size comma 0. Weights 1 square braces 0 dot size gives the number of hidden neurons, and hidden layer dot assign initializes the hidden layer with 0 values. Now I'm going to loop through each neuron in the input layer and compute the values for each neuron in the hidden layer. So here I'm going to say for size underscore t equals 0 and I less than weights 1 dot size and I plus plus. And we have another loop for size underscore t j equals 0 and j less than weights 1 square braces 0 dot size and j plus plus. And here we say hidden layer square braces j plus equals input square braces I times weights 1 square braces I square braces j. Well, we're not done yet. For each neuron, we need to add its corresponding bias and then apply the ReLU activation function. Here's how it looks in code. For size underscore t j equals 0, j less than hidden layer dot size j plus plus, and hidden layer square braces j equals ReLU, and we pass it hidden layer square braces j plus bias 1 square braces j. And this ensures that negative values are replaced with 0 while keeping positive values unchanged. In the next step, I'm going to initialize the output layer. Vector double output weights 2 square braces 0 dot size and 0. Now I'm going to compute the values for the output layer. Just like before, I loop through each neuron in a hidden layer and each weight in weights 2. For each connection, I multiply hidden layer value by its corresponding weight and accumulate the result in output. Okay, let's do it. For size underscore t, I equals 0 and I less than weights 2 dot size and I plus plus. And here we have another loop for size underscore t j equals 0 and j less than weights 2 square braces 0 dot size and j plus plus, and output square braces j plus equals hidden layer square braces I times weights 2 square braces I square braces j. This is the weighted sum that will be passed to the activation function in the next step. In the next step, I apply the activation function to the output layer. I loop through each output neuron at its corresponding bias and then apply the sigmoid function. So we say for size underscore t, j equals 0, and j less than output dot size, and j plus plus, and output square braces j equals sigmoid, and we pass it output square braces j plus bias to square braces j. This helps introduce nonlinearity and scales the output between 0 and 1. Finally, we return the output vector, which holds the network's predictions after applying the activation function. So here I'm going to say return output. Next, we create the predict method. Vector double predict, and it takes vector double input, and inside the method we say vector double hidden layer, and it will return forward, and we pass it input and hidden layer. Now let's talk about training the neural network using backpropagation and gradient descent. We'll create the train method, which takes the input data, the target's values, a learning rate, and the number of training epochs. So here we say weight train vector vector double inputs, and vector vector double targets, and double learning rate, and finally end epochs. This method will adjust the weights and biases to minimize the error, the difference between the predicted value and the actual target, and improve the network's predictions over time. Here, the input is a vector of input samples for XOR. The target is the expected values for each input. The learning rate is a small value that determines how much to update weights during training. And the epochs is the number of times the model will go through the entire dataset. Now we start training the neural network. We loop through the number of epochs, which determines how many times the neural network will process the entire dataset and update its weights. And here I'm going to say for int e equals 0, e less than epochs, and e plus plus. The more epochs we run, the better the model learns. However, if we train too much, it can lead to something called overfitting, but we're not gonna cover that in this video, maybe in another one. Next, we initialize total loss to 0, and here we say double total loss equals 0. This variable will keep track of the total error across all training samples in the current epoch. Later, we'll use it to monitor how well the network is learning over time. And this loop for size underscore t, I equals 0, and I less than inputs, that size, and I plus plus, iterates through all training samples. And here we create a hidden layer vector, vector double hidden layer. This initializes an empty vector that will hold the values of the neurons in the hidden layer after forward propagation. In the next step, we compute the output using forward propagation. Vector double output equals forward, and we'll pass it inputs, square braces I, and hidden layer. Next, we calculate the loss using the mean squared error function, which measures the difference between the predicted and target values. And here we say double loss equals mean squared error, and we pass it output and targets square braces I. Then we add it to total loss to track the overall error for this epoch. So total loss plus equals loss. Next, we prepare to compute gradients for back propagation. We create a vector with the same size as the output layer to store the gradient values needed for weight updates. And here I'm going to say vector double output gradients and output dot size. We then loop through each output neuron for size underscore t, j equals 0, j less than output dot size, and j plus plus, and calculate the gradient using the difference between the predicted output and the target multiplied by the derivative of the sigmoid function. Here's how it looks in code. Output gradients square braces j equals inside parentheses output square braces j minus targets square braces I square braces j, and times sigmoid underscore derivative, and we pass it output square braces j. Now we need to create a vector to store the gradients for the hidden layer with the same size as the hidden layer itself. So here we say vector double hidden gradients hidden layer dot size, and we should loop through each hidden neuron to compute its gradient based on the output gradients and the weights. So let's do it. For size underscore t, j equals 0 and j less than hidden layer dot size and j plus plus. First, we initialize hidden gradients j to 0. Hidden gradients square braces j equals 0. In the next step, we loop through each output neuron for size underscore t, k equals 0, k less than output dot size, and k plus plus, and accumulate the gradient by multiplying the output gradient with the corresponding weight. Hidden gradients square braces j plus equals output gradients square braces k times weights to square braces j square braces k. Then we multiply the gradient by the derivative of the real u function. So here outside this loop, I'm going to say hidden gradients square braces j times equals real u underscore derivative, and we pass it hidden layer square braces j. This is because the real u function has a derivative of 1 for positive inputs and 0 for negative inputs. So for neurons that are active, the gradient stays the same. For inactive neurons, the gradient is blocked and doesn't contribute to error, which helps us efficiently adjust only the active neurons. Next, we need to update the weights and biases for each weight in the output layer. So we say for size underscore t, j equals 0, and j less than weights 2 dot size, and j plus plus. And we have another loop for size underscore t, k equals 0, and k less than weights 2 square braces 0 dot size, and k plus plus. And we adjust each weight by subtracting the product of learning rate, the output gradient, and the corresponding hidden layer value. Here is how it looks in code. Weights 2 square braces j square braces k minus equals learning rate times output gradients square braces k times hidden layer square braces j. And this is how you make the network learn from its errors and improve its predictions. Also, we need to update the biases for the output layer, and we say for size underscore t, j equals 0, j less than bias 2 dot size, and j plus plus. For each bias, we subtract the product of the learning rate and the corresponding output gradient. And here we say bias 2 square braces j minus equals learning rate times output gradients square braces j. This ensures that the biases are adjusted to reduce the error in future predictions. Next, we update the weights for the hidden layer, and we say for size underscore t, j equals 0, j less than weights 1 dot size, j plus plus, and here we have another loop for size underscore t, k equals 0, k less than weights 1 square braces 0 dot size, and k plus plus. And for each weight in the hidden layer, we subtract the product of the learning rate, the hidden gradient, and the corresponding input value. And here we say weights 1 square braces j square braces k minus equals learning rate times hidden gradients square braces k and times inputs square braces I square braces j. This helps adjust the weights in a way that reduces the error during training. Finally, we update the biases for the hidden layer, same as the output layer. And we say for size underscore t, j equals 0, and j less than bias 1 dot size, and j plus plus. Next, for each bias, we subtract the product of the learning rate and the corresponding hidden gradient, like this. Bias 1 square braces j minus equals learning rate times hidden gradients square braces j. And also, this adjusts the biases to minimize the error in future predictions. And the final part of the training method, we want to print the current epoch number and the average loss every 1000 epochs. And here we say if e mod 1000 equals 0, cout epoch e and loss colon total loss divided by inputs dot size and int L. This helps us track the progress and see how well the network is learning over time. Now let's move on to the main function. This is where we'll set up our neural network, provide training data, and run the training process. And here I'm going to say int main, curly braces, return 0. First, we create an instance of our neural network. Neural network, and I'm gonna call it NN 2, 3, 1. Here, we specify that our network has 2 input neurons, 3 hidden neurons, and 1 output neuron. Next, we define the training data for the XOR problem. This consists of 4 input pairs, each with 2 values representing all possibilities combinations for zeros and ones. So we say vector, vector, double, inputs, and here we have this data. A 4x2 matrix. Then we define the target outputs for the XOR problem. Each input pairs has a corresponding expected output. 0 when both inputs are the same, and 1 when they are different. And here we say vector, vector, double, targets, and here we have this data. A 4x1 matrix. Okay, let's train the model and see if it can learn the XOR pattern. And here I'm gonna say nn.train, and we're gonna pass it inputs, targets, and we set the learning rate to 5%, 0.05, and training for 3000 epochs. And here we print a message to indicate that the training is complete. And we say cout/n training complete. And we have another /n here. Or you can use int l like this. Now I'm gonna print a message to indicate that we are about to display the predictions after training. Cout predictions after training, and int l. Finally, we loop through each input in our dataset and pass it through the trained neural network, and showing the input values along with the network's predicted output. And here we say for const auto reference operator input :inputs, and inside the loop we say vector double prediction equals nn.predict, and we pass it input. Then we print the results. Cout inside double quotation input open square bracket and input square braces 0, and inside double quotation comma and input square braces 1, inside double quotation close square bracket arrow prediction and we have prediction square braces 0 and int l. Okay, let's run the code and see what we have. As we can see from the output, the loss decreases over time, indicating that the model is learning and improving. After the first epoch, the loss is this, and as we continue training, it reduces significantly. By the 1000th epoch, the loss drops to around 0.031. By the 2000th epoch, it's even lower at 0.0016. And this shows that the network is successfully minimizing the error with each epoch. And after training is complete, we can see the predictions for each input. For the input 0 and 0, the prediction is this, which is close to the expected output of 0. Similarly, for the input 0 and 1 and 0, the network predicts values close to 1, as expected. Finally, for the input 1 and 1, the prediction is this, again matching the expected output. These results show that the model has successfully learned the XOR function. Before we finish, let's test our model with new input. And here I'm gonna say vector double test underscore input equals, and I'm gonna give it 0.1 and 0.9 because I want to see how it performs on unseen data. Then we say vector double prediction equals FNN.predict, and we're gonna pass it test underscore input. Next, we need to print the results just like before. Okay, let's run it again. Now we have tested our model with the unseen data, the input 0.1 and 0.9. The model uses the weights and biases it learned during training to make a prediction. In this case, the output prediction is this. This shows that the model is generalizing well, applying what it has learned from the XOR data to make predictions on new unseen inputs. And that's it for today's video. We have successfully built, trained, and tested a simple neural network in C++ to solve the XOR problem. If you enjoyed this video and found it helpful, make sure to hit that like button, subscribe to the channel for more deep dive tutorials, and also ring the bell so you won't miss any new videos. If you have any questions or suggestions, feel free to leave a comment below. I'd love to hear your thoughts, and thank you for watching this video.